ready then? Welcome to the ACE Preparation League. In this live session, I'm going to take some concepts of Fourier Transform. So I'll be taking a rectangular pulse and I'll be finding its Fourier transform. After this, I'll be using this rectangular pulse and its Fourier transform to find Fourier transform of other signals. So now it's like something like I have taken 10 problems, okay? So I'll try to solve those 10 problems using the rectangular pulse. This is something like Kamal Hassan acting in Dashavtaram. He plays 10 different roles, okay? In all those roles you will see Kamal Hassan. In the same way, in all those 10 problems, you will see this rectangular pulse playing the role of Kamal Hassan, okay? So let's start this discussion. So what are they asking here? They gave us x of t, it's 1, for modulus of t less than 1, elsewhere it's 0. They also provided its Fourier transform, which is 2 sine omega by omega. Find the Fourier transform of the following signals. Okay, so they gave us various signals like this. These are the various signals. We need to find Fourier transform of all these signals using the rectangular pulse. First, we will analyze the rectangular pulse, we'll find its Fourier transform, and then we'll try to solve the other problems. So, let me first take a rectangular pulse. This particular rectangular pulse is from -1 to 1. Let me take a general rectangular pulse. So something like this. So let's take a rectangular pulse like this, which is from, let's say, -t/2 to t/2, whose amplitude, let's say, is A. Before I find its Fourier transform, I would like to write its width as well as the area. Now what's the width of this rectangular pulse? The width of this rectangular pulse, like you can see it's from -t/2, t/2, so obviously the width is capital T. What's the height? It's A. Now what is the area? Area is simply this width into the height, okay? So what's the area? The area is, the height is A, the width is capital T, so it is simply AT. So this information will be useful to us. So what I'm going to do now is, I'm going to find its Fourier transform. How do you find Fourier transform of any signal? So this is how I find Fourier transform of any signal. Integral -∞ to ∞, x of t e power minus j omega t dt. So this is how I find Fourier transform. You have to substitute this into this, simplify, see the end result. Let's substitute and see the end result. Like you see, the limits are from -∞ to infinity here, but the signal is only from -t/2 to t/2. So no need to write from -∞ to infinity. Just write it from -t/2 to t/2. It's A e power minus j omega t d omega. Now if you see this in the description, he already gave the Fourier transform as 2 sine omega by omega. I just want to like derive it, or I want to find the Fourier transform, do some generalization. Okay, that's why I'm doing these calculations. A is a constant, you can put A out. So this is A out. The integration of e power minus j omega t by minus j omega, and the limits are -t/2 to t/2. Now you try to simplify this. So let's try to simplify this. If I substitute the limits, what do I get? A e power minus j omega t/2 minus e power minus j, okay, omega into minus t by 2, okay, whole divided by what? Whole divided by minus j omega. So you try to simplify this. So this is like minus of minus is plus. So if I take this minus to the numerator, so you will see some simplification. So I would like to write like this: a by omega. I've taken minus to the numerator, so this is like e power j omega t by 2 minus e power minus j omega t by 2 whole divided by what? J. Now I want to multiply and divide by 2 so that I can write this in terms of sign. So let's write this. Let's multiply and divide by 2. So 2a by omega equal to e power j omega t by e power j omega into t by 2 minus e power minus j omega t by 2 whole divided by 2j. Now you can see this 2 and 2 get cancelled and you get the same thing. The interesting part is this highlighted part is like e power j theta minus e power minus j theta by 2j. This is nothing but sine theta. How much is this? This is sine theta. So let's write that. How much is this? This is sine theta. So let me write it on the next page. How much is this? This is sine theta. So now what I have is 2a by omega into sine theta. What is in the place of theta? Omega into t by 2. Omega into t by 2. I want to do a few more like modifications to this. Like I'll multiply and divide by t. So this is something like 2at by omega t sine omega t by 2. I'll take this 2 to the denominator. So this becomes at by omega t by 2 sine omega t by 2. Now let's write these two terms together. So this is something like at sine omega t by 2 by omega t by 2. Earlier I pointed out that the area of this rectangular pulse is at. I said the area of this rectangular pulse is at. The width of the rectangular pulse is capital T. Let's try to write this result in terms of area of the rectangular pulse and the width of the rectangular pulse. So what do I get is, here I have area. Area of what? Area of the rectangular pulse into sine, okay, omega t by 2 by omega t by 2. Now look at this. This t by 2 is nothing but the width of the rectangular pulse by 2. This t by 2 is nothing but the width of the rectangular pulse by 2. Check this. What did we write here? So what did I write here? The width as capital T, right? What do you see here? You see t by 2. So this is width of the rectangular pulse by 2. So how do you remember this? If you want to find the Fourier transform of a rectangular pulse, then it is so simple. It is area of that rectangular pulse into sine omega into width of the rectangular pulse by 2 by omega into width of the rectangular pulse by 2. So we have a notation here which is very simple. So whenever you have like this sa x stands for sine x by x. See here I have x, the same x is sitting here, the same x is sitting here. This is just a shorthand notation for sine x by x. I can write this in the form of area into sa omega into t by 2. So finally this is the Fourier transform of the rectangular pulse. This is the Fourier transform of the rectangular pulse. Now what is given to us? They have given something like this. Rectangular pulse from -1 to 1 with the amplitude 1. This is what is given to us in a time domain. And they have also provided its Fourier transform as 2 sine omega by omega. Let's use this logic. Let's verify whether that is correct or not. It's the area of the rectangular pulse into sa omega into t by 2. Okay. So its Fourier transform is area of this. Here the width is 2, the height is 1. So it's 2 sa omega into width by 2. Width is 2, half of that is 1. That means simply sa omega. So what is sa omega? It is simply 2, like you have 2, so I am retaining that, 2 sine omega by omega. So I have verified. You might be thinking like it's already given, why this fellow has again calculated. No. And I want to generalize. This is for -1 to 1. In general, any rectangular pulse is given. How do you find its Fourier transform? This is how I find the Fourier transform. So this is the main guy in this today's discussion. With the help of this rectangular pulse and its Fourier transform, I'll be finding Fourier transform of various signals. Let's start with this first one. What is this? This is again a rectangular pulse, okay, which is from 0 to 2 with amplitude 1. Now most of the students, what they do is they'll try to apply that formula. That is applicable only when the rectangular function or the rectangular signal is symmetrical about y-axis. This result is applicable only when it is symmetrical about y-axis. Is this symmetrical about y-axis? No. This is not symmetrical about y-axis. Don't apply that. Then what are you supposed to do is, can you write y1 of t in terms of x of t? Can you write in terms of x of t? I can. So what is x of t? X of t is given in this following way, that is -1 to 1 with amplitude 1. This is x of t. Okay, this is x of t. What's the relation between this and this? How can you express y1 of t in terms of x of t? That's the question. If you shift this towards right by 1 unit, you get y1 of t. Check it. You shift this towards right by 1 unit, you get y1 of t. So if I shift, let's see, when I shift this, yes, this is 0, this is 2, this is 1. So what is this? This is simply x of t minus 1, right? So what is y1? Y1 is simply x of t minus 1. That means if you know the time shifting property of Fourier transform, you can easily find the Fourier transform of y1 of t. Okay. So what is the time shifting property here? So I'll also be revising the properties here. Okay. So two things simultaneously you will be learning. One is how to use this rectangular pulse and find the Fourier transforms, and the other is like a recap of the properties. So if x of t, Fourier transform is x of omega, what's the Fourier transform of x of t minus 1? It is e power minus j omega t naught into x of omega. Okay, so here let me generalize. X of t minus t naught Fourier transform is e power minus j omega into t naught into x of omega. This is a Fourier transform. What is this property called? This is called time shifting. Time shifting. Now what you have to do is compare what is t naught. T naught is 1. So substitute, and what do you think is the Fourier transform now? The Fourier transform is very simple. So let me write the answer now. It's e power minus j omega. What is t naught? It's 1. So just leave it, e power minus j omega into x of omega. Do you know what is x of omega? It's given in the problem, and we have also calculated it. That is 2 sine omega by omega. So 2 sine omega by omega. So the first one is done. And I have discussed the time shifting property in Fourier transform. Let's go to the second one. And if you find any alternate way of solving this, you please try. You can post your answers in the comment. I will definitely reply in the comment. Either in the live chat or below the YouTube video you can comment. They have given us a triangular pulse. What they gave? Triangular pulse. And they are asking us to find Fourier transform of this triangular pulse. The most important thing is, try to note these observations. What is the width of this triangular pulse? The width, it's 4 units. The width is 4 units. What's the area of this triangular pulse? It's half, base is 4, height how much? The height is 2. So what's the area? The area is 4. So things like this, will be definitely a very important thing for finding Fourier transforms. The width is 4, area is 4. So here they have given a triangular pulse from -2 to 2. Let's look at the Fourier transform in general. Okay, let's look at the Fourier transform of this triangular pulse. That means I don't want to take from -2 to 2. In general, suppose, okay, so let's say I just want to derive a generalized result. So how do you derive a generalized result? I'll show you. So the main idea behind this is, let's take a rectangular pulse like this, which is from -t/2 to t/2, let's say with the amplitude A. Let's take another rectangular pulse, -t/2 to t/2 with amplitude A. Let's convolve this. If you convolve two rectangular pulses, of equal width like this, the result is a triangular pulse. So how do you draw that triangular pulse? From where does the triangular pulse start, right? Where it ends? We need to know these observations. If you want to know these observations, then you have to learn convolution. The rules of the convolution say that when you convolve these two waveforms, look at their lower limits, -t/2, -t/2. The lower limit here is sum of these two, that is -t/2 plus -t/2. It's -t. So it's -t here. And if you want to find this end point, then you have to add this two. t/2 plus t/2 is capital T. This is capital T. And you will have a triangular pulse like this. This is the triangular pulse. Now how do you find the amplitude here? What I said is slope is a square. I did not say that the amplitude is a square. I said slope of the line is a square. If you know the slope, you can find that amplitude. How? I'll tell you. So this is like -t, 0. This is 0, y, because this is origin, na? Okay. So this is 0, y. You have 2 points in front of you. You have the slope. So what's the slope? Change in y, that is y minus 0, by change in x, that is 0 minus of -t. This must be equated to what? A square. So what is y? Y is a square into capital T. That means this amplitude level is a square into capital T. So let me remove this now and then mark a square into t. How much is this? This is a square into t. So the important information was, if you convolve to rectangular pulses of equal width, the resultant is a triangular pulse. Okay. So why am I saying all this? We want Fourier transform of this triangular pulse. What we want? We want Fourier transform of this triangular pulse. Let me write the width and the area of this triangular pulse. So what do you see here? What's the width? The width here is like from -t to t, that is 2t, na? The width is 2t. What's the area? The area of this triangular pulse is, so how do you find area of a triangle? Half base into height. So it's half base, that is 2t, height a square into t. So 2 cancels. What is left over is a square t square. So these observations are important. I'll tell you why these observations are important. Actually, the focus is about Fourier transform of a triangular pulse. The focus is about what? The focus is about Fourier transform of a triangular pulse. I'm trying to find the Fourier transform of this using the rectangular pulses. Okay, using our Kamal Hassan, we are trying to find Fourier transform of this. Convolution in time leads to multiplication in frequency. Okay, convolution in time leads to what? Multiplication in the other domain. So let's apply Fourier transform on both sides. What happens to this? You have to multiply the individual Fourier transforms. So now we have the Fourier transform of the triangular pulse. Because I'm applying Fourier transform on both sides. Fourier transforms applied here. So we are applying Fourier transform on this So you'll be applying Fourier transform on this as well. Okay, Fourier transform on this as well. The Fourier transform of convolution of this two is simply the individual Fourier transforms product. So what is the Fourier transform of this? It's a very, very simple result. It's area of this rectangular pulse, which is AT sa omega into width by 2. The width here is capital T, so it's width by 2, capital T by 2, into, this is again the same fellow, so you just take this. So this is AT sa omega into T by 2. So 80 into 80 is 80 whole square, okay, 80 whole square into sa square into omega T by 2. Now 80 whole square or a square t square is same as the area of the triangular pulse. So finally I got the Fourier transform of the triangular pulse, because we applied Fourier transform on both sides. The Fourier transform of this is same as the Fourier transform of this. So you got this expression. Now what do you see from this? This is area of the triangular pulse. What is this? T by 2. Here we wrote width as 2t, but what you see is t by 2. That is 2t by 4. You see 2t by 4. What is 2t by 4? It's t by 2. Now we can generalize this result. We can generalize this result and we can write this as area. Area of what? Area of this triangular pulse into sa square into omega into width by 4. Okay, width by 4. So you can use this now general result, area of the triangular pulse into sa square, okay, omega into width by 4, width of the triangular pulse by 4. Now let's try to answer this question. What is area here? The area is 4. So what's the Fourier transform? It's 4 sa square omega. What's the width? 4. I said width by 4. 4 by 4 is 1. It is just sa square omega. So what you get as 4. You know what is sa omega? Like I said, like sa x is sin x by x. So this is nothing but square omega by omega square. Okay, so this is how you find the Fourier transform of a triangular pulse. Again, whatever we have got, this is applicable when the triangular pulse is symmetrical about y-axis. Okay, so let's see the next one. You see y3 of t. Y3 of t is given like this. How do you find the Fourier transform of this using the rectangular function? Okay, so let's see how do you express. First of all, what is given? This is what is given. Minus 1, 1, this is 1, this is x of t. We want to express y3 of t in terms of x of t. We want to express that so that we can use the Fourier transform of the rectangular pulse to get Fourier transform of this. Observe this. This looks like a straight line that is passing through origin, and this is up to like from minus 1 to 1 only. That means if I multiply t with this, you get this. So let's do that. Y3 of t is simply t into x of t. You can see x of t is only from minus 1 to 1. It's only from minus 1 to 1. When you multiply that with t, obviously you get this shape, na? Obviously you get this shape, because how does t look? T is something like this, a straight line passing through origin. What next? How do you find Fourier transform of this? Right? So we have an interesting property, and that property is as follows. If x of t Fourier transform is x of omega, then t into x of t Fourier transform is dash. It is j d by d omega of x of omega. This property is called differentiation in frequency, or simply times t property. Times t because you are multiplying t with x of t. Times like multiplication with t, okay, times t means. You can also call this as differentiation in frequency, because you see the d by d omega of x of omega. So I'll just write, this is called P property. So what's the answer? The answer is so simple. It is j d by d omega of x of omega. X of omega we already know, 2 sine omega by omega. So the Fourier transform is j d by d omega of 2 sine omega by omega. So you have to simplify this. So finally, I got the Fourier transform of y3 of t. So using what? Using rectangular pulse. Let's see a few more things. So I have a sine pi t function here, which is only from -1 to 1. Okay, which is only from -1 to 1. How do you find Fourier transform of this? So let's see how do we find Fourier transform of this. Again, our reference is the rectangular pulse. This is our reference, which is from -1 to 1 with amplitude like this. This is x of t. If you multiply sine pi t with x of t, then you get a resultant signal which is only from -1 to 1. Okay? If you multiply sine pi t with x of t, the resultant is only from -1 to 1, because x of t is only from -1 to 1. So I got the idea now. So y4 of t can be written as what? X of t into sine pi t. So now what property we are going to use to find Fourier transform of this? Let's see what's the property. This is called modulation property, which is one of the most important thing for communication. Okay, communication subject. So let's see what is that property about. If x of t Fourier transform is x of omega, then x of t, so let's see, x of t sine omega naught t. What's the Fourier transform of x of t into sine omega naught t? So the Fourier transform is given by 1 by 2j, okay, x of omega minus omega naught minus x of omega plus omega naught. So this is called the modulation property. What is this called? This is called the modulation property. Now, if you compare, in the place of omega naught, we have pi. Let's write the Fourier transform of this. X of t into sine pi t Fourier transform is 1 by 2j x of omega minus pi minus x of omega plus pi. Now you can substitute what is x of omega minus pi and x of omega plus pi. So let's substitute that. So this is like 1 by 2j 2 sine omega minus pi by omega minus pi 2 sine omega plus pi by omega plus pi. So finally this is the answer for the question. So what is the property that I have used? I have used modulation property. The property that I have used is called modulation property. So we have few more signals to discuss. So let's discuss them one by one. So I have two impulses here. How do you find Fourier transform of this? And what is our reference? Our reference is that rectangular pulse again. So what is that rectangular pulse? The rectangular pulse is like this, which is from -1 to 1 with amplitude 1. So this information is given and its Fourier transform is also given. How do you express y5 in terms of x of t? That's the discussion. You see that it's a constant here. It's a constant here. The derivative of a constant is 0. The derivative of a constant is what? It's 0, na? Right? So you see 0 here. And at -1, there is a jump from 0 to 1. There is a jump from 0 to 1. So this is like a discontinuity. And also at 1, there is a jump from 1 to 0. There is a jump from 1 to 0. So what happens to the derivative? If you perform the differentiation, what you get? So because of this discontinuity, the derivative of this leads to an impulse like this. this is at minus 1. So impulse like this. Because of the discontinuity here, like at 1, this leads to a discontinuity impulse like this. Okay. So you see this Wi-Fi is same as this. So how did you get this? By differentiating. By differentiating what? Differentiating x of t. So now which property I'm going to use? I'm going to use the differentiation in time property to find Fourier transform of this. So let's see what is differentiation in time domain. Let's see what is differentiation in time domain. X of t, Fourier transform is x of omega. Then what's the Fourier transform of d by dt of x of t? It is simply j omega x of omega. It's a very simple result. So now if you know the Fourier transform of x of omega, you can easily find the Fourier transform of d by dt of x of t. So what's the answer? The answer for the present question is j omega into 2 sine omega by omega. So this is the answer for the question. So let's go to the next one. And what is this property? This is differentiation in time. Differentiation in time. How do you express this in terms of x of t? That's the question. How do you express this in terms of x of t? So let's check it. What is x of t? X of t is the rectangular pulse like this, which is from minus 1 to 1 with amplitude 1. This is the information given to us. If you can express y6 in terms of x of t, then you can easily find Fourier transform of y6 of t. How do you express that? That's the that's the main idea. How do you express that? I'll write like this. y6 of t is integral minus infinity to t x of tau d tau. Meaning by, if you integrate this, you are going to get y6 of t. Right? Surprised, na? If you integrate this, you will get y6 of t. Students will ask, how? How integrating this will give this? I'll just verify at some points just to get some confidence here. For example, let me check with this. What is y6 of minus 2? I already know that from this graph, y6 of minus 2 is 0. I want to confirm that. Okay, I want to confirm that. For that, I'll integrate from minus infinity to what? Minus 2 x of tau d tau. Okay. So what is x of tau in this interval minus infinity to minus 2? It's 0, na? Look at x of t, na? Right? X of t or x of tau, the same waveform. There is no signal. It is from minus 1 to 1. So there is no signal in this interval. So obviously this is 0. The integral will also be 0. The integral is 0. I already said from this graph that y6 of minus 2 is 0. So there is no doubt in this. I have to verify a few more points, then only the confidence comes. So let me verify at minus what? Maybe 0. So before I verify, this level is 2. So this is like 1. So I already know that y6 of 0 is 1. I just want to do the verification. So what is y6 of 0? According to this relation, it is minus infinity to 0 x of tau d tau. Now you see this waveform is from minus 1 to 1 only. So there is no meaning in integrating from minus infinity. Okay, you just change the limits like minus 1 to 0. So let's change the limits. Let's change this limits. The limits are minus 1 to 0. X of tau, okay, from minus 1 to 0, it's 1. Or simply, you find the area from minus 1 to 0 because integration is involved, na? Integration is involved. How do you find area? So that too I want from minus 1 to 0 only. So how do you find this area? This area, it's like a rectangle again. This width is 1, the height is 1, the area is 1. Width into the height, na? So I got my answer. Here it's 1. Is this matching with this? Yes. You want to verify a few more things? Okay. So let me verify with what is y6 of, let's say, 3. From this graph, let's say 3 is here. Y6 of 3, that is the value of y6 at t equal to 3 is how much? It's 2. So let's see whether we get it or not. Minus infinity to what? Minus infinity to 3 x of tau d tau. Now you observe x of tau or x of t, which is only from minus 1 to 1, right? So there is no need to integrate from minus infinity to 3. So you just change these limits. Even you can write like this, minus infinity to minus 1, it's 0, minus 1 to 1, it's 1, okay, and then from 2 to 3, it's 0, nah? So no need, just integrate from minus 1 to 1. Integrating from minus 1 to 1 is equivalent to taking area here. What's the area? Area of a rectangle. So from minus 1 to 1, width is 2, height is 1, so it's 2 here. It's matching, right? It's matching. Now you take any point, it will match. We got a relation between y6 and x. What's the relation? They are related through integration. So now you people are supposed to know what is integration in time property. What is integration in time property? Let me write it here. Integration in time. If you know x of t Fourier transform as x of omega, what's the Fourier transform of minus infinity to t x of tau d tau? What's the Fourier transform of this? Let's write the Fourier transform of this. It is x of omega by j omega plus pi x of 0 into del of omega. This is the Fourier transform. You substitute, okay, x of omega, because we already know x of omega, now it's just 2 sine omega by omega, so we got the answer. What is this property called? This property is called integration in time. This is called integration. Let's proceed. So I have another signal in front of me. So you might be comparing y7 with y1. How are they different? Here y1 is having a width 2 units. The width of this pulse is 2, na? Whereas y7 is width 4. This is different. Okay, y7 and y1 are different. So how do you find Fourier transform of this? Again, our reference is this point. Point is the rectangular pulse which is given to us, which is from minus 1 to 1. Okay, this is our reference. We'll use this and we will try to express y7 in terms of x of t. How do you do that? First, I'll shift this towards right by 1 unit. Let's shift it. Let's shift this. Let's shift this pulse towards right by 1 unit. So you get 0, this goes to 0 and this goes to what? 2. What is this? This is, right, I said expanded. So this is the expression for that, x of t by 2 minus 1. Finally, y7 of t is in terms of x of t is as follows, x of t by 2 minus 1. What next? What are the operations involved here? One is shifting, the other is time scaling. If you know how to deal with this, then you can easily find Fourier transform of this. So let me explain you both the properties. Like time shifting is already covered. It's a Fourier transform of x of t minus t naught. It is e power minus j omega t naught into x of omega. What's the Fourier transform of x of at? This is called time scaling property. It is 1 by modulus of a, x of omega by a. These are the two properties that you have to use for solving this question. So what are the things involved? Shifting and scaling. So see how we are going to find the Fourier transform of y7. So let's first find the Fourier transform of x of t minus 1. How much? It's e power minus j omega x of omega. What next? The scaling x of t by 2 minus 1. Like I said, x of a t Fourier transform is 1 by modulus of a x of omega by a. So we'll use this. If you compare in the place of a, if you compare in the place of a, you have a 1 by 2. In the place of a, you have what? 1 by 2. So this is like 1 by a na. So 1 by 2 x of omega by a. Wherever you have omega, replace with omega by a. So this is something like this, e power minus j omega by 1 by 2, which is like 2 omega, x of omega by a. A is, like I said, 1 by 2, so this is 2 omega. So finally what you get is 2 e power minus j 2 omega x of 2 omega. So this is the Fourier transform of y7 of t. You know what is x of omega, right? It's 2 sine omega by omega. You can easily get x of 2 omega from that. So far we have calculated Fourier transforms of 7 signals with the help of this rectangular pulse. Let's see a few more. How do you find Fourier transform of this? What I'll do is, I'll take y2 of t as my reference. So where is this? I take this as my reference, minus 2 to 2, right? Here the amplitude is 2. For this, I already know the Fourier transform. Okay, I'll use this to find Fourier transform of this. I'll first write this is minus 2, this is 2, this is 0, this is 2, this is y2 of t. We'll utilize this, we'll try to express this in terms of y2 of t, and we know the Fourier transform of y2 of t. So it means like if you can express this, that means you have almost solved the question. Focus on this particular part first. This particular part. How do you generate this from this? Now observe that it has got a width 2 units, whereas this has got a width 4 units. That means there is a compression involved. You have to compress that. So before doing that compression, what I'll do is I'll first shift this towards left and then I'll compress. Shift by what? I'll shift by 2 units. So if you shift this towards left by 2 units, what happens? A triangular pulse like this, which is from minus 4 to 0. So here it's 2. So here we have a important thing. Here the value is specified as 1 and the y2 of t is the value here is 2. So you have to take that also into the consideration. Right? I want the width to be 2 units only, that too from minus 2 to 0. So I have to compress. Firstly, what is this? This is y2 of t minus t plus 2. Now left side I have shifted. So y2 of t plus 2. After this, what I am supposed to do is I have to compress it. Not just compression, I should also take care of this factor. So I'll divide it with 2 and I will also compress. So what I am going to get is something like this. I'll first write the expression. So it's 1 by 2. Why 1 by 2? To counter this 2. I need 1 na. So 1 by 2 y2 of this time compression. So it's 2t plus 2. So the highlighted part here, so there is a minus sign. So let's see what's going to happen. I would like to write it directly because instead of shifting towards left, you have to shift towards right. And there is a minus sign also involved. So if you want to, let's see what's the Fourier transform of this particular signal. This is 0, this is 2, and this is minus 1. This is simply minus 1 by 2 y2 of 2t minus y2 of 2t minus 1 by 2 times, okay, minus 1 by 2 times y2 of 2t minus 2. In the earlier problems also, we have seen how to deal with shift as well as time scaling. So I would like to leave this to you. Okay, I'll leave this to you. You have to find the Fourier transform of this. So I've already expressed y8 in terms of the known ones. You have to apply Fourier transform now. So in the earlier problems, we have discussed how one has to do this. There's a shift involved, there's a time scaling involved. Here also the same thing. There's a shift involved, there's a time scaling involved. So try to do this. And if you find any other way, new ways of expressing or finding its Fourier transform, please do comment. We'll be very happy to see your answers. I can even verify your answers and I'll reply you back. Okay, you put it in the comment section. How do you find Fourier transform of this? Okay, so how can you express this in terms of the rectangular function? Let's check this. Now this is from -2 to 2. Let me take a rectangular pulse. Let me take a rectangular pulse which is from -2 to 2. Which is from -2 to 2. Let me take the amplitude as 1. Okay, this is a rectangular pulse from -2 to 2. I would also take a triangular pulse which is from -2 to 2. So I've taken a rectangular pulse and a triangular pulse like this. Let's indicate this as 1. If you subtract this 2, you might get this. If you subtract this, you might get this. Let's check. Do I get this or not? How do you do this? Just a subtraction. If you know subtraction addition, this course is going to be very, very simple. So how do you subtract the things? Let's say this is -2. Let's say this is 0. Let's say this is 2. Okay. How do you do the subtraction? At -2, its value is 1. At -2, its value is 0. What is 1 minus 0? It's 1, na? It's 1, okay. At 0, its value is 1. At 0, its value is 1. Subtract, na? 1 minus 1, 0. So let me highlight this point. At 0, it's 0. At 2, it's 1. At 2, it's 0. Okay, what is 1 minus 0? 1 minus 0 is 1. So I got few points. Let me take one more point like this, maybe 1 here. At 1, it's 1. At 1, how much is this? It's not 1. This is 0.5. So what is 1 minus 0.5? 1 minus 0.5 is 0.5. So something like this. Here also you'll get same thing, right? So this is how it looks. Yes. If you subtract this 2, you are going to get this. If you subtract this 2, you are going to get this. Find Fourier transform of this, find Fourier transform of this, and then subtract. Okay? So let's find the Fourier transform. Now this is a rectangular pulse, this is a triangular pulse, whose results we already know. What's the area of this? Width into the height, na? What's the width? The width is 4. Height is 1. The area is 4. So it's 4 sa omega into width by 2. Width is 4, 4 by 2 is 2. So this is 4 sa. Width is how much? It's 4. Width by 2 is 2. So it's sa 2 omega minus. How do you find Fourier transform of this triangular pulse? It's area of this triangular pulse. How do you find the area? Half base is 4, height is 1. Okay, half base into height, na? So what's the base? Base is 4 units. Height is 1. The area is 2. Okay, area is 2. So here it's 2. Sa omega by 4. What's the width? Width is 4. 4 by 4 is 1. That means I got the answer. We got the Fourier transform of this in just one step. Right? So see how useful is the rectangular and triangular pulses. So let's see this problem. How do you find the Fourier transform of this? Try to express this in terms of the previous ones. Try to express this in terms of the previous ones. So let me show you how to express this in terms of the previous ones. There are multiple ways of doing this. If you get any, like if you can solve in a different way, you can solve it. and you can post your answers. So let me show you how to solve this. So the signal is from -2 to 2. Let me mark few points. So what I'm going to do is, I'm going to add few things, and I'll try to get this. Add what? I'll add triangular pulses like this. Check this. This is the first triangular pulse. Let me add a few more. This is the other triangular pulse. If you add this, what happens, right? So let's check this. Adding this, will it really give this? So I'm trying to add. From -2 to -1, you see a signal like this, na? From -2 to -1, there is no signal here. From -2 to -1, there is no signal. When you add the 3, you get this, okay? You get this. So let's draw the resultant here. So this is -2, this is -1, 0, 1, and then this is 2. From -2 to -1, you have to retain this. Okay, I'll retain. From -1 to 0, what happens? -1 to 0. From -1 to 0, this is decreasing, whereas this is increasing. Like for example, here it's like 1. Okay, so here it's 0, na? So let's take this also 1. Let's mark this also 1. Now see, at -1 its value is 1. At -1 its value is 0, and here also it's 0. You add 1 plus 0 plus 0, it's 1. Okay, it's 1. Okay, fine. Let's say at this particular point, let's say its value is 0.9. Here it's like 0.1, and here there is nothing. So when you add, again you get 1. So you get 1 like this, that is a constant like this. Okay, because this is decreasing and this is increasing, and they maintain a constant level. Okay. Now 0 to 1, there is no signal here. 0 to 1, this is decreasing, whereas this is increasing. Again, a constant will be maintained. Again, a constant will be maintained. So like this, up to what? 1. From 1 to 2, there is no signal here. From 1 to 2, there is no signal here, but from 1 to 2, there is a signal like this. When you add, you get this as the result. So yes, this as the result. Now you see this? Y10 is now expressed in terms of this triangular pulses. In terms of the triangular pulses. You can find Fourier transform of this triangular pulses. So you get Fourier transform of this. Now how do you write this in terms of the previous results? Let me show you how do you write this. Let me also highlight that this is -1, this is 1, okay. So this is 1, 0, 2. Now earlier there was y2 of t. There was y2 of t. Let's see what was y2 of t. Y2 of t was something like -2 to 2, right, with amplitude level 2. But here, like this is from -1 to 1. Okay, this is from only -1 to 1. So you have to compress it, and you have also take care of this. So how do you do this? I'll write the result here. This is 1 by 2 y2 of, I said compress, so it is 2t. This particular part is 1 by 2 y2 of 2t. In the same way, you have to express this in terms of y2. You should also express this in terms of y2. Let's express this. How do you express this? Let's solve this in the new page. This is the reference -2 to 2. So this was our y2 of t. If you can find expression for this, then this is very, very simple, because here you are shifting towards left, and here you will be shifting towards right. So what I'll do is, first I'll shift this towards left by 2 units. If you shift towards left by 2 units, you get a triangular pulse like this, minus 4 to 0. So here it's 2. So what I'll do is I'll also try to divide this by 2. Okay, so this is like 1 by 2 y2 of t plus 2. But I just need from minus 2 to 0, na? So I'll compress this. So if I compress this, 1 by 2 y2 of compress, so it's 2t plus 2. How does this look? This looks like this. This is from minus 2 to 0 with this 1. Now we know the expression for this, that is 1 by 2 y2 of 2t plus 2. Let's write this. How much is this? 1 by 2 y2 of 2t plus 2. In the same way, can we directly answer this? Or you want me to do all this? This is not needed, because same operations, but instead of shifting towards left, we have to shift towards right. Okay, so let's see this. What's the expression for this? This is 1 by 2 y2 of 2t minus 2. Finally, what is y10? Finally, what is y10? Y10 is sum of all this, na? That is 1 by 2 y2 of 2t plus 2 plus 1 by 2 y2 of 2t, na? Plus 1 by 2 y2 of 2t minus 2. What are the things involved? The things involved are, look, shift, scaling, right? And then this amplitude also you have to take care. So we know the Fourier transform of y2 of t. Try to find the Fourier transform of this. The properties that are to be used are time shifting and time scaling. So far, what we have done, we have taken one rectangular pulse. Look at this. We took a rectangular pulse like this. We calculated its Fourier transform. With the help of this rectangular pulse, we have solved, like, let's say, some problems, right? So in all those problems, we tried to express the given signal in terms of rectangular function. So this rectangular function is one of the most important signal in this Fourier transform. I hope you people have understood all these problems. If you get any other, like if you are able to express it in any other way, you please try to do that, and you can post your answers below the video. I'll just reply it.